All right then, let's look at df. df is composed of an x and y component. There is the x component of df, and I will call it dfx. And here's the y component of df, that is dfy. And I would like to make a good description of df. Now, and then in terms of df, I can describe dfx and dfy. So df is the force produced on my victim charge by the environment charge dq over here. And I know the expression for the force of a point charge on another point charge, and certainly dq being infinitesimally small is close to being a point charge. So here is the scalar expression for df. This tells me the magnitude, or the length, of the df vector, given the size of the charge dq, and the size of the victim charge q, and the separation between them, r, which you can see is squared right here. That's r squared. And there is our constant, 1 over 4 pi epsilon. So this is the value of df right here. And but df is now described in terms of dq and r. Now r is the distance from here to here, and that distance will be changing as I move my little point charge up and down there. Well, when I move the little point charge up and down, I will need to have some kind of a parameter that tells me how high I've moved it up and down, and we'll take that distance to be y. So from here to there, we'll call that y. That means that I'm now able to describe the size of df in terms of r, but if I look at this triangle, I can also describe r in terms of y. In fact, later I'm going to want to find the size of dfx, and as you can see from this triangle, if we call this angle alpha, then that angle in here is also alpha, and the component of fx, the component fx, is the side adjacent to the angle alpha, and so that would be given by the cosine function. So dfx is equal to df cosine of alpha. So dfx is df cosine of alpha. That means that in order to describe dfx, clearly I would need to be able to describe alpha, or cosine of alpha, and to describe df. Df is described up here, and it's described in terms of dq and r. Well, if I look at all of those things, I see that dq is a variable, r is a variable, and alpha is a variable. So if I were going to try to do some kind of an integration at this point, I would be integrating over the variables q and r and alpha. And that's going to be a problem because you don't know how to integrate over multiple variables. I don't think multivariable calculus is not on your slates, at least for most of you. So the question is then, how can I describe df and alpha and r in some kind of common language in dq? Well, let's look at the r and the cosine alpha. Those can be described easily in terms of this triangle. And that's here. That picture is here. So we see that if I've taken y to be the distance from the origin up to the point dq, if y is that distance there, then this triangle is y on that side and x on this side, and the angle alpha is in here. So r, by Pythagoras, is the hypotenuse of this triangle and is given by x squared plus y squared, square root. That gives me r. Then cosine of the angle alpha, here's the angle alpha, cosine would be the side adjacent divided by the hypotenuse. So here is the side adjacent divided by the hypotenuse r, like that. But we have an expression for r, so x over r can be written as x over x squared plus y squared, square root, because this piece is r. All right.